In this video, we are going to code backpropagation. Okay, so in the previous video, I talked about backpropagation in terms of like if I turn this variable, how is my output variable affected? In this video, let's first talk about why the algorithm is called backpropagation. Okay, so for that, I have this thing over here, right, in my screen. You see that this thing we did it before. I'm basically calculating f. Okay, and this thing, right, that I did calculating f, this is also known as a forward pass. Okay, that means that I am going in this direction, so downwards, and then I'm calculating the value of f. It's pretty simple. We can actually look at this over as a graph as well, and we already did this in our previous video as well, so let's just do that again. Okay, so for our reminder, so force actually comes from mass and acceleration. Acceleration is a division of velocity and by time taken. Velocity is a division of distance by time taken, so that's pretty simple. And then the way the computation works is looks something like this. Wait for it. So I know that my so I go to the bottom of my tree, right, and I say that I know that s is a t and t is a 1, right? So I can do this calculation to get v as a 10, okay, and then t is still a 1, so I can do this calculation to get a as a 10, right, and then m is a 3, and then I know my force will become 30. Okay, so over here in the graph, what we essentially done is the forward pass. Okay, so what else do we do? Now we need to figure out how each of the variable affects force, right? And that we did that using partial derivatives, right? So calculating partial derivatives. Okay, so the first thing I'd have to calculate is how my force is being affected by my force. Okay, that turns out to be a 1. So I start at the top, okay, of this tree, and then I have to do that computation backwards. Okay, so why is it this backwards? So if you look at this code over here, then the first thing I'd do is I'd look at it for the force, then I'd look at it for the mass and acceleration, then I'd have to go back to acceleration, do it for v and t, and so on. Okay, so that is why this is known as a backward pass. And because we are calculating how these variables like tweaking this variable would tweak the output in the backward direction, this algorithm is called backpropagation. Okay, so enough of that talk. Let's actually go ahead and program this. Okay, so when we program this, what do we program? Okay, so look at this over here. Okay, I have this tree structure over here, right? So tree structure is a good data structure to actually code this. So let's do it in terms of this tree structure. What do I see in a tree? The first thing I see is a node. Okay, so let me code a node over here. Okay, what are the things that I need in a node? Okay, so let's look at that. So whenever we look at nodes in a tree, it's better to look at the most leaf node. Okay, so in leaf node, I see that I need this value right over here. So this is literally the value for that node. Okay, so let me code that out. So def under init, and I'm interested in this thing called value for the node. Okay, just making sure that I don't. Okay, now I have the value for the node. So great, that's a great start for the node. And now I'm able to create an instance of that node. So n is a node. I need to give it a value, let's say 10. So I say this node is s because we're just looking at the leaf node. And yeah, I can do that now. Okay, that's good. What else do we need in that node? Okay, what else do we need? So first thing, let's look at what that node looks like. If I do this, then I see this gibberish. So instead of this, let's change this. The way you would change that is by overriding a function called representation, short form REPR, and then you're going to return a string over there, which I'm going to format, and I'm going to say this is a node which has a value of self.value. Okay, what this does now is I get a clean representation of that node, so that's good. What else do we need? Okay, So over here, if I look at that node, I don't really need anything more there. But let's look at this other node now. If I look at this node V, then you'd realize that this V node actually comes from the division, okay, of this node and this node. Okay, so that means this V node, okay, this V node has childrens. So let's actually encode that as well. So this nodes can have children. Is children, where does that children come from? I'm gonna feed those children into the node. So that's pretty simple. And okay, cool. And this S node, okay, if I look at it, nothing. So S dot children, okay, so that looks good now. So I can do children now, and I see I don't have any childrens for S, but if it were a V, I would have childrens, right? Great, now we have a notion for the childrens, okay. And here's something interesting, okay. If I look over here, then V is actually S divided by T, right? Okay, so if I were to represent the M, S and T as a node, okay, right, let's say this is a node, this is a node, and this is a node. I have to run this code and then this code. Oops, what's that? Yeah, so it says that I cannot divide node and node. So let's actually allow this node to also have a division. So how would you divide a node? Okay, and the way you can do that is overriding something called TrueDiff function. Okay, and it takes in two parameters, self and other. So the way you can think of self and other is over here. Let's just look at this example of V, right? So V is basically the division of S and T, right? So over here, when you write this out, you'd write it this way: V is equal to S divided by T, right? So over here, this guy over here will be the self, this will be the other, okay. So how you did divide the node? Okay, the way you do that is you'll return a node, and the value of that node would be self dot value divided by other dot value. Okay, so that's good. Okay, and this thing that we return over here, okay, so what is that? That's a V, right? And what are the children for V? Okay, so children for V are S and T. So I should probably encode that over here by saying my children are self and other. Remember, self is S and other is T in this particular case. So good, I have that notion now. So instead of this, let me ignore the, okay, let's not ignore this, let's just remove that. Oh, oops, okay, let's just remove that node definition over there. Oh, why is this thing not deleting? Interesting. Okay, oh, it's not deleting. Yeah, whatever. So let's just say this is S, right? Value of 10, T node value of 1. Okay, so now what I'm able to do is I'm able to say V is S by T, right? Whenever I do this division, I'll call this function, and then this node will be V. Okay, so let's see what V is. V is 10. Okay. Now I don't have any notion that tells me that what happened. Okay, what happened to get that V? So over here, that is represented as a slash. So let's also include that in our node. So let's call it operator, right? We need to understand what operation happened. So let's just call it OP for operation. So I'm gonna give that in over here. And for a leaf node, the operation would be nothing. So that makes sense, right? And over here, when I do that division, right, my operation would be a division. Okay, and let's also have that over here. So operation is self dot operation, and so this would now look a bit more cleaner. So I have this operation that tells me that this value that I obtain from a division. Okay, that's cool. What else? Okay, next thing is I have to encode acceleration, which is v by t. I can do that and get my acceleration, so no problem. Again, v by t is basically v is a 10, t is a 1, so you don't see any difference in the output, but I can calculate a, right? So the next thing I want to calculate is f, which is m times a. Now I don't have an m, so I should encode my m over here. So m is basically a node, okay, and the value was 3. So I can do f is equals, I want to do f is equals to m times a and print f, but node and node cannot multiply. So let's allow this node to be multipliable. So def underscore underscore mul is the operator overload for that. And I need to have self and other. So let's look at this one again over here. So I would need two things. So the thing I want to find is my force, obviously, and that is done by a multiplication of m and a. Okay, so that makes sense. Yeah. So if I want multiplication, then okay, over here the way you would write that is again f is equals to m times a. So in this case, right, m will be our self, a will be our what now, other. Yeah. So we got our self, excuse me, and our other. So let's create a new node for that. Self dot value multiplied by other dot value, right? That's the value. What's the children? The children would be self and other again. What's the operation? Operation is a multiply. So now we should be able to do that multiplication, and nope, I should run this and then that, and now it works. So we have a node that has a value of 30. Great. So so now we have essentially done this forward pass, but we have this structure now. It's kind of like the tree structure, right? We're maintaining in terms of node. Great. Now we want to perform a backward pass. Okay, backward pass. So to do backward pass, what we did over here was, the first thing we did was we calculated df by df, which is basically 1. This is always a 1 for the topmost node. Okay, so let's do this now over here. But now I realize something, right? So this thing over here that I calculated, okay, this is the derivative, right? And I have not stored that anywhere. So where should I store it? Okay, so if you realize, then if you realize something over here in this node, right, this thing is a variable that affects the output. Okay, f can affect our output f. Okay, m can also affect output f, right? A can also affect output f, right? So this thing that we calculate, right, these derivative, we should store these derivatives in the node itself. So let's store the derivatives in the node. Okay, now I'm going to introduce a new term. So instead of talking about derivative, I'm going to call derivative as a gradient. Okay, so it's not a big confusion, right? We're just saying that whatever the value we get after we compute the derivative, that we're calling as the gradient. Okay, it's pretty simple. It's just a name. So self dot gradient, that's how I want to store my gradient. Okay, so in the initial case, right, when we didn't do any of the forward pass, what should our value of the gradient be, right? We don't know what the gradient here is, nor we know over here, not here, not here, not here, not here. So we should probably just set it to 0. Okay, because 0 meaning that I don't really know what that gradient is. So that works out well, and I can do this now, and everything still works out well. Okay, And let's now do the first form of backward pass, which is this f dot gradient should be equal to 1, right? And this is always going to be a 1. Does that make sense? Okay. Okay, what is the next step? Next excuse me. So the next step is to look at this thing. Okay, again, let's look at this graph over here again. So I calculated df by df. The next immediate step for me would be to calculate df by dm. Okay, because that's easy, right? And m really does not depend upon anything lower than that, so I can compute that. So let's compute that. Okay, and we already computed it before, right? Df by dm is gonna be equal to a, so acceleration. Okay, that's easy. So I can say something like m dot gradient is equal to what? A, right? So whatever a dot value is. Does that make sense? So I can do that, but there's a problem here, right? So if I do it this way, then I would have to manually assign gradients for each of the nodes, right? I have to manually do that, and instead I would like to use this tree structure over here that we get going, right? And I want to think in terms of the children for my f. Okay, so if I think in terms of my children, let's look at this node over here, right? So what we are doing is we're doing a multiply, right? So over here, when we do this creation of node, let's say this is our result, right? And then we return that result. Okay, that makes sense. And I want to do something, right? Whenever I do a back propagation for this node f, right, I want to look at its children, and then I want to calculate the gradient for each children. Okay, great. So it turns out that whenever you do a multiplication, right? So over here, this case is a multiplication, right? So whenever you do a multiplication, it turns out that if you want to find the gradient of m, right, that is always gonna be the other thing, the value of the other thing, right? So how would you do that then? So for that, we need a way to say that node, okay, I want you to back propagate. So I want instead of doing m dot gradient is that and a dot gradient is m dot value, right? Instead of doing this, what I want to do is I want to do something like m dot back propagate. Okay, so when I do f dot back propagate, what I expect is all of the children of f, right, should be back propagated. Like it should automatically calculate the gradients for the children of f. Okay, and if I want to do that, I need a function here. So the function would be back propagate, right? And here I want just the self, and I want it to somehow figure out how to back propagate. Okay, so what I should do is I should first look at this thing that I'm doing. If it is a multiplication, then the way I would back propagate is I would just assign the values of the opposite nodes, right, to each other. But if I do that, then for every single operation I should have a case over here. Okay, so for example, I need to check if self dot op is equal to a multiply, and then have some logic over here, right? And then I also need to do if self dot op is equal to a divide, then I need to have some logic over here. So instead of doing that, we're gonna use a hack. And that hack is basically, so whenever I do a multiplication, I also attach a backpropagate function to this node. Okay, so how does that look like? Okay, for that, in this node, right, I am gonna store a backpropagate function. Okay, and then I'm going to take that backpropagate function from over here, propagate, and I'm going to assign that backpropagate function. Yeah, instead of doing this, let's just do it this way. So let's just make backpropagate as none, and then over here when I multiply, I set that backpropagation function. Result dot backpropagate is equal to, so let's set it as a backpropagate function, and I'm gonna define that function over here, propagate pass. Okay. So let's look at what that should be like. So the first thing I need to do is I need to do df by dm. If you remember, m over here is the self guy, and I need to find out df by da, which is m. If you realize dA over here is the other thing, so what I should be doing inside this function is I should say something like this: self dot gradient. That's what I want to set when I do a backpropagate. So I want to say it is equal to what now? So if self is m, then I would like to assign it to other dot value. Okay. And if self dot the other dot gradient would be self dot value. Okay. So here's something very, very important we need to understand in this case. Okay. When we are looking at this node f, right, multiplied ma, if you realize df by df is a 1, right, and df by dm, so df by dm would be a, okay. But in case when the parent node, this f over here, does not have a gradient of 1, okay, the actual way to calculate the gradient would look something like this: df by dm is equal to df by df into df by dm, which is 1 times a. So just because the df by df is 1 over here, right, it does not matter, okay, to not include df by df, okay. But if this node f, right, was somewhere in the middle, then it would matter for this df, this term over here to be included, because it would no longer be 1. So what I should really do over here is I should apply chain rule and say whatever the result is, remember f is the result, whatever this result is, I want the gradient for that result to be included when I calculate the gradient for self. Okay, same thing over here, result dot gradient times self dot value. Okay, so that's an easy backpropagate function, so that's good. And now I can do this. I can make that gradient a 1, and then I can do backpropagate. Node has no okay, so what I should do over here is this backpropagate is not existent. It should be underscore backpropagate, and I should run this code over here before I was supposed to do that. So great, now we have backpropagated, right? And if you check, I can get m dot gradient, which is 10, which is the value of acceleration that's supposed to be 10, so that's right. A dot gradient, which is a 3, which should be a value of m, so that's correct. So great, we have done a backpropagation for a single node now, and that has a multiplication. Okay, so let's look at another node. So another node would be acceleration, which is a division of v and t. Okay, so if you look at this particular node, I am interested to do a backpropagation over here as well. So this is df by da, which is basically the gradient. You remember that, right? And we have already computed that gradient over here because we did a backpropagate on f. So what I want to do over here is I want to do a dot backpropagate. Okay, and when I do that, I get a problem saying that you cannot call backpropagate. Remember, we assigned backpropagate to none. How did you get that a? That a was a division, right? Division of v and t, right? And when we are doing division over here, I have not defined the backpropagate function. So I should define that backpropagate function. So let's define that backpropagate function over here. And that is result is equal to, and I want to return that result, and I want to say result dot backpropagate function should be a backpropagate function, and I'm going to define that function over here. So that makes sense. Pass. And okay, now let's try to figure out what should be the value, okay, for self. Okay, if you realize, right, this is written as a is v by t, so over here this guy is the self and this guy is the other. So let's try to find out what the values for the gradient should be. Okay, what should df by dv be, or what should df by dt be? Okay, so let's find that out. Okay, so we already know how to do that, okay, because of the fact that we now know chain rule and we know partial derivatives, we can figure this out. Okay, so the way you would figure this out is we know how f is being affected by a, right? That is basically this thing over here. So that is gradient for a, right? This is basically a dot gradient. So that's easy. And this thing should be multiplied by how a is being affected by v. Now we don't know this yet, but we have a way to calculate that, right? We already did that before, so let's calculate that. And let's do it by hand. So dA by dv is basically limit as h tends to 0, the function of v going plus h, and the function of v by h. Okay, and if you realize the function of v over here is basically a is equals to v by t, right? So v by t, and you remember that t over here is a constant. That's because we're doing a partial derivative. So that means f of v plus h should be v plus h by t. And with that knowledge under our belt, I'm gonna do this very, very fast now because we are experts in calculating derivatives. So v plus h by t minus v by t by h, limit as h tends to a 0, I can do 1 by t times h and have that computation over here. v goes away. I can can basically say h also goes away, so I can basically do this. So just to avoid confusion, I won't do that into h. H1's are h, and you get 1 by t. Okay, so you get dA by dv is 1 by t. V over here is the self. Okay, so that means self dot gradient, what should it be? It should be the gradient for, okay, now result in this case is our acceleration, remember, right? So whatever the gradient for acceleration is, that is result dot gradient. I should multiply it with whatever this thing is supposed to be. So remember, t over here is the other, so I should have 1 divided by other dot value, right? So that makes sense. Now let's look at what df by dt is supposed to be. This is also supposed to be how f is being affected by a multiplied by how a is going to be affected by t. Okay, this thing over here, again, we know that's a dot gradient, or in our case the thing that will be a resulting node, right? That's that gradient. We can calculate this thing over here because we are experts in calculating derivatives. So let's calculate that. dA by dt is limit as h tends to 0, the function of what again? T plus h minus the function of t, the function of t divided by h, and acceleration is basically v by t, and the function of t is again v by t. Remember, this time v is a constant. That's because we're doing a partial derivative. So that means f t plus h the function of t plus h should be v t plus h. So let's plug that in over here, right? And this is what now? v by t plus h minus v by t, divide the whole thing by h, and I am gonna go a little bit quick over here to do that calculation. 1 by 1 plus t minus 1 by this thing, limit as h tends to a 0, v by h, I can do that quickly, divided by t plus h multiplied by a t, tt goes away, limit as h tends to a 0, v by h into h by t, t plus h. I'm gonna go h away. I'm gonna put that h as a 0, and I'm gonna get negative. This thing is a negative, right? So I'm gonna get negative t and t plus 0, which is basically minus v by t squared. So I get acceleration being affected by time is negative v by t squared. Okay, so let's represent that. Remember, t over here is the other thing, t over here is the other, v over here is the self. So to encode that, I should say other dot gradient, right, is result dot gradient multiplied by whatever this thing evaluates to be. So v over here is the self, so self dot value, and divided by other dot value, and that should be squared. And that's how you would backpropagate division. I think it looks good, so let's do it. Run that, run this, do that gradient, do that backpropagate, and do that backpropagate, and it looks good. So over here in the tree, right, let's not lose the track of tree. I'm not gonna add in that operations just for the sake of easiness, right? So we are over here, we did a backpropagate, so it should backpropagate the gradients for v and t. Okay, and if I see v dot gradient, I see it's a 3. Yeah, that's good. T dot gradient, I see negative 30. So that's good as well. And now let's do a backpropagate on v as well. So I can do v dot backpropagate, and I will get the value for s dot gradient, right? And sorry, t dot gradient. Now here is an important thing. So t over here, right, it appears in 2 different places, right? So that means this thing t will affect the f, can affect the f in 2 different ways. Okay, so the first one was with respect to acceleration, right, and the second one was with respect to velocity. Okay, so the way we actually talked about this in a previous video as well. So because t appears 2 times, its gradient is not actually, so the gradient over here is negative 30, the gradient over here is negative 30, right? So the actual gradient for t should really be 30 plus minus 30, which is negative 60. So this over here is now wrong. So that means I should fix that. So how do we fix that? And the way we do that is, I just said we add it, right? So my node over here, right, whenever I compute gradient, it should be plus equal. Okay, so I'm going to do a plus equal over here and over here as well. Okay, so this actually is for every single variable in the in our tree structure, right? So that's why I'm adding a plus equals over here and here as well. So great. So if I run everything again now, right, this gradient, this backpropagate, this backpropagate, and this backpropagate, and then if I calculate s gradient and t gradient, now the gradient for t is correct. So this way, we have now a way to do a backpropagation, right? But we've been doing this backpropagation very manually. So let's try to have an automation for that as well. Okay, so how would you do that? So let's do that. So let me just remove all of this, right? Actually, I shouldn't have removed it because we want to take in reference of what we are supposed to do. Okay, so let's say that the way you do a backpropagation, right? over here. What I want to do is I just want to invoke backpropagate on my root node, which in this case is f, right? And then I want all of my children to have its gradient filled. Okay, that's what I want. So let's do that, and the way we would do that will look something like this. So I am going to define a backpropagate function over here, and the logic for this function, right, this thing should have a self over here, and the logic for this should be that over here I should go to every single children, right, and then I should call backpropagate, right? That's what we are supposed to do. So let's try to do that. How should we do it? Okay, the first thing we want to do over here is whichever node I'm at, right, which is my f node, I want to set the gradient for that node as, okay, so self dot gradient, I want to store it as 1. That's the first thing we did over here, right? Next is I want to call this underscore backpropagate on the current node, right? And that would backpropagate for my children. Does that make sense? So over here I want to do a self dot backpropagate. So that's cool. And now I want to go in its children, right? So I want to go in the children, and I want to call backpropagate for those children as well, right? So yeah, so what I should do is I should probably say something like for child in self dot children, I want that child to also do a backpropagate. That makes sense? That kind of looks like what we did over here, but that would only backpropagate for this f, right? So look at this over here. So I have my f, m, a. So this algorithm will only backpropagate for f. So f, it will set the gradient for f as a 1. It will backpropagate for this, right? And it will go over here and over here. So this thing would be set to the gradient, which is 10 and a 3, and then over here v and a t. So it goes to its children, and it does call backpropagate. So the backpropagation for v also will be over here, but then v over here still has its children, right, which is s and a t, and the backpropagation now does not work for s and a t. Okay, so this algorithm is incomplete, not incorrect, incomplete. It does not incorporate anything below over here. So what we should try to do is, let's try to do it in such a way that we do it for all the nodes in the system. So we have to do it, we can do it, I think, in a recursive manner. So let's think, okay, how can we do this recursively? So if I am at this thing over here, right, if someone just sets the value as 1, right, what I can do is I can look at all of my children, and I should do a backpropagate for each of the children, right? So I should call this backpropagate function recursively. Does that make sense? So instead of calling this backpropagate, if I call this backpropagate, will it do the work? Okay, it does not do the work, because then I would be setting self.gradient for every single one of the childs. So what I should do is I should have another function. So let's call that backpropagate recursive. And what this will do is this will give you a root. Okay, so from this root, okay, let's say I want to backpropagate, then I will go to the child, I'll do a backpropagate, I'll go to a child, I'll do a backpropagate recursive, okay, and I will do that all the way over until I reach a leaf node which does not have any child, so that won't do a backpropagate. I think that logic should work. Okay, so I say self dot backpropagate recursive and use self as the node. I think that should work. I think. Not sure. So let's test it out. I go over here, I go over here, so I don't need to do this anymore. All right, I can just come over here and say f dot backpropagate, and this should more or less work. So let's see if it works, and it does not, obviously. So it says that node object does not have backpropagate. Okay, so when you reach the end node, so in this case S and a T, right? So for S and a T, because these are raw nodes, these things do not have the backpropagate function defined for them, right? So over here what I should probably say is if self dot backpropagate, which is if I have that function, if I have that thing defined, then I should backpropagate, otherwise I shouldn't do it. So I think this should work now. Oh, look at that. This thing should not be self, this thing should reference root, right? Because we're doing it for root. So whatever the root that you give us, that is the thing, that is the node in which we want to do the backpropagation. So we do that, we do this, we do this thing without doing any of these. So let's see if it works now. And it does not. Node object has no attribute backpropagate. Why would you say that? I did that, I did this, and I did a backpropagate, and this function inside of backpropagate function, when I try to do recursive, oh right, my bad. So this thing should not be a backpropagate, this thing should be backpropagate recursive, because you want to recursively do the backpropagation. Is that correct? For that child, is that correct? I think it is. Yeah, I don't think I need to specify that root over here, because that root and the self is basically the same thing in this case. So this is basically child dot backpropagate. Don't need to pass in anything over there, and this just needs a self, right? So over here this function is basically needed to set the current, for example, if I am the root node, and then I just need to set my f as a gradient 1. I don't need to do all of that, and it should work. Hopefully it does work and I don't get ashamed. And nope, none type is not callable. I actually did that check, this if statement check, because it could be a non-type, and it just says that if it is a non-type it's not callable, bro. How pitiful. Look at that problem that I just, my god, I'm an idiot. Look at this. This self.backpropagate references this, right? And I should have referenced this variable over here. What an idiot I am. So now it should work, and it does. So this is goes to show you how like mind-bending recursions can be. Okay, so I do backpropagate and I am expected to see the gradients for each of my nodes. And so what I should do is I should say f dot gradient, which is a 1, that's correct. M dot gradient, which is a 10, that's correct. A dot gradient, which should be a 3, that's correct. And then we have V dot gradient, that should be a 3, that's correct. T dot gradient, it's a negative 60, that's also correct. And what else do we have? S dot gradient, that's a 3, that's correct. So we have successfully implemented backpropagation, and that too in terms of recursion. So that's good. That's great. Okay, so let me remove these now. So let's also do this. I don't want to look at the gradient, like do it every single time, right? So let's actually have a function that can print all of my entire tree, right? And printing the actual tree would be very hard. So let's just print the nodes of the tree in order. So let's do that. Let's try to do that. So def print nodes, and I need to give it a root, and this is the function I want to print the nodes for. So let's actually look at what this function should do. So I am at f a m v t s and t, right? So I start at my root node, which is f. I should print this. I should go to my child. I should print this. I should go to my, okay, I go to other child. I should print this. I should go to other child, right? And then print this. So let's define this in terms of in a recursive way. So I will be changing my representation to include a gradient. So my gradient would be self.gradient. So that's good. This is good. The backpropagation is good. And here's how you would print it. So I print myself, right? And then I go to my children for child in root.children, and I say print underscore nodes for that child. And that's a recursive definition, and we will stop when we no longer have childs. I think they should work. So let's see if it works. So print nodes for f, and it does work. So this guy over here is the f, this is m, this is a, this is v, right? This is s, this is t, and this is t. So yeah, we have a way to print stuff now. So great. So this is basically how we implement backpropagation algorithm, and we did this specifically in Python. Now this thing that we did, right, for backpropagation, this is gonna be our building block when we build our neural network. Now just to excite you, right, this thing that we have just done, right, we have encoded backpropagation, we have already started coding neural networks. And this thing that we did, this engine that we have for backpropagation, this is going to be our basis for building neural networks, and that we'll do in other videos. So great, see you.